Well, this is a history of anodizing, and I can't make it the history of anodizing because that would take probably at least a day to present that. But anyway, this is a history, meaning that what I'm going to cover is essentially going to be Western Hemisphere anodizing and so on, developments with aluminum and et cetera. All right, so there will be it's very easy to say that there's a parallel history, and I'll explain this in a minute here as we go through this, but there will be a parallel history in Europe and the European continent that will go along with what is happening here in the United States, but there is an overlapping between the Europeans and the U.S. and it's a common thing, it's a common thread that passes through our total history here in the United States. And then later on, we will find that there is a third avenue of history that tangents this along in Japan, in Asia, so that there's also three processes of anodizing that are taking place and developments and so on that are occurring. To begin with, the anodizing or the aluminum process was something that was developed through the efforts of Charles Martin Hall and simultaneously Paul Louis Toussaint Hérault in France. And they developed their processes and they applied for their patents about 3 months apart in 1887. And in 1888, the USA granted Charles his patent, and in France they granted Hérault his patent. And needless to say, there was some tit for tat over who had the rights to whatever, and it was finally decided by the international courts the US would get their rights and Europe would get their rights, and that's the way it would be. So Charles got the rights to his patent and his production of aluminum and reduction process. And he joined with a company called Pittsburgh Reduction Company, who was willing to finance his process. And then they proceeded to produce aluminum through bauxite. And the formation, and I'll explain this a little bit, but the aluminum that was produced was pure aluminum. And they learned to alloy it and so on, but the bottom line is that they were just marketing aluminum to aluminum consumers who took the aluminum and they did various things with it, and they had many different applications. And one of the interesting ones that was an application was in 1901, the Pittsburgh Reduction Company actually formed an aluminum cooking utensil company. So we went through this scare several years ago about, oh, cooking with aluminum was terrible and it's Alzheimer's and all this kind of stuff and so on, but yet cooking utensils with pure aluminum, this is unfinished aluminum, it wasn't Teflon coated, it wasn't hard anodized or whatever, it was just as is aluminum. And people used it all the time. And there were other things that were done that were household, bathtubs, kitchen sinks, and so on. So they did all kinds of stuff with aluminum at that time. So it was going so well that they ended up forming a company in Canada, which became Northern Aluminum Company Limited in Montreal, Quebec. And then eventually in 1907, then the PRC reorganized and became the Aluminum Company of America. So that's how we came into the Aluminum Company of America, which still has its headquarters in Pittsburgh, Pennsylvania, and its technical headquarters in New Kensington, Pennsylvania. Then eventually, the Northern Aluminum Company changed their name to Aluminum Company of Canada, and eventually Alcoa divested itself of that company, and it became a separate Canadian company, and eventually it would become the Alchem that we are aware of today. So all of this has transpired during this period of time. And the process itself is very simple in the sense that you take bauxite and you dissolve it into cryolite, you pass a special electric current, direct current, through the anodes, which then picks up the oxygen and releases aluminum ion to migrate to the cathode and form aluminum metal. And pure aluminum metal is insoluble in the cryolite, so it falls to the bottom of the cryolite, and then it gets drawn out into crucibles, and then it gets poured into various types of ingots, or it goes to furnaces where it's alloyed and cast and so on into various products for either rolling applications or extrusion. Now, rolling and extrusion applications at this time were limited in terms of extrusion capabilities. They didn't have a lot of those, but the rolling capabilities were readily available, and they did use that, and I'll get to that. So what happened is that they were using bauxite, which is high in iron and silicon. So the alloys, or the aluminum, was not that pure. So then Bayer came up with a process whereby the bauxite is digested. The insoluble, most other metals are insoluble and caustic, so they all fall out as insoluble materials. And the clear solution is then piped over. The aluminum hydroxide is precipitated out. It's then calcined or heated to the point where the water is driven off. And then we have aluminum oxide, in granular form, which then is readily soluble or dissolvable in the liquid molten cryolite. So this is essentially the process. And the interesting part about this is that for the first 40 years of the history of aluminum, no metal finishing was done. People tried to paint it, the anodizers tried to, platers tried to plate on it, and so on, but with zero success. So therefore, these years were all years of where raw aluminum, unfinished aluminum, was out there in the workplace, in the consumer industry, and in a variety of places. They could use automotive, even aerospace mainly after World War I got involved. The big thing that they found was that the electrical transmission properties of aluminum were wonderful. And so it started to replace the copper industry as transmission lines. And the cookwares we talked about, some construction products and so on where they could be forged or worked up in some capacity. There were some construction uses of aluminum and so on. Also, but the automotive is interesting because of the talk that was done, the talks that were done today about automotive uses of aluminum. And it's interesting to note that even back in the 20s, that aluminum was used in various early automotive applications as the automobile was being developed. Charles Martin Hall died at a very young age. He was 52 years old. He died from a special disease that was unique, and not because of the work that he had done with the cryolite and with the aluminum and so on. But at the time of his death, he had become a multi-millionaire, which his chemistry professor that he had taken chemistry under and had talked about the person who isolates aluminum on a commercial quantity basis will become a millionaire, and he did. And this was over a period of about 27 years that he became a millionaire. So this is a lot of aluminum. Millions and millions of pounds of aluminum were out there in the industry, in commercial applications, in a variety of applications, just within that period of time. Part of his estate, he got his degree at Oberlin College. I went there at one time, and anyway, I'm sorry, The History of Charles Martin Hall is available, this book, made of aluminum. You can find it on eBay, it's available on eBay. I got mine for 50 cents, you can see there. It's a little more expensive on eBay. But there's a lot of history about aluminum and related to the companies, the company histories, and also the Oberlin College website. Okay, this is Sophronia Hall, which is a fine arts hall auditorium. And this is the dedication that was made by him. And he also bequeathed a sum of money that was to be used in perpetuity for maintaining certain aspects of Oberlin College. Okay, so that's Alcoa, all right? Now, in the 20s, people were smoking tobacco from, I don't know what, the 1700s. They came over here and found that the Indians were growing tobacco and smoking it, and it became popular. But the bottom line is that in the early 20s, R.J. Reynolds Tobacco Company existed, and people were smoking like crazy. and they were producing the cigarettes. But they needed foil to protect those cigarettes, to protect them. So they were using tin foil that would be rolled out on special presses and so on, and the tin metal would be wrapped around the cigarettes, and that's the way they used it. However, he had a nephew, R.S. Reynolds, and he decided that he was going to replace the tin with aluminum, because aluminum now having become quite popular. He then created a company forming U.S. Foils, and he took the rolling equipment and made it so that it was sufficient to roll out aluminum instead of tin, which is the aluminum being a harder metal. But he found a way to do that, and he ended up coming up and developing, building a rolling and foil plant in Louisville, Kentucky, and Reynolds Metals Company came into existence. This is important later on. Then eventually, after the war, Kaiser Aluminum and Chemicals Incorporated came into being about 1945, shortly after the war. It was over. So at the time so about this time, and not counting Kaiser, of course, but the four major aluminum companies that eventually were developed in the United States and Canada became the Alcoa, eventually Alcan, but Aluminum Company of Limited of Canada, Reynolds, and Kaiser. Now, as far as anodizing, the anodizing processes did not actually begin until the 20s, late 20s. The first actual anodizing process was chromic acid anodizing, and this was a patent that was developed and approved in 1923. And it was done in England, and it was for, England was already developing airplanes with wings that were made of aluminum and fuselages made of aluminum. And the consequence of that was that they needed some corrosion protection. And so these people, Bengough and Stewart, came up with this process by which they would anodize the aluminum sheet stock in chromic acid. And it's interesting to note that today that same basic chromic acid procedure is what's in the military specs and is in the aerospace specifications and so on, and is used today as the chromic acid anodizing process. There are obviously some modifications that are made with more sophisticated equipment and everything, but the bottom line is that it's still done, and it's done for the same reasons for the aerospace applications. So the other major commercial anodizing process, and I've said this before, that probably anything that ended with the word acid on it was tried at one time or another for anodizing purposes. And certainly over the years, that's been the case. But in this case, the actual first sulfuric acid patent was done developed in 1927 and approved in 1928. So this was the first patent. And the interesting part of this is it was with Gower, O'Brien, and others in England, okay? And it introduced process capabilities for coloring. Even at this time, they were looking at what the prospects would be for coloring the anodic coating, okay? So, the interesting part is, and here's where Europe and the United States get together, they tried to market or license their anodizing process in England, and they may have even tried other countries in Europe, but the bottom line is no one wanted it. No one wanted it. So they ended up coming to the United States, and they sold the rights, not a license, they sold the rights to the patent to a company called Aluminum Colors in Indianapolis, Indiana. So the actual first anodizing was not done in England or in Europe. The first anodizing was done in the United States. This is a copy of that sulfuric acid patent. It's available. You can just Google anything. And by the way, in the paper, if you get my paper, which is an 8-page document here, at some point when you get your electronic readouts, I have included patents and references to patents and all kinds of reference information, because I didn't have space to do that here. But this is the copy of the original patent that was granted for the sulfuric acid anodize. And in it, it talks about adding certain metal salts to the anodizing process that would lead to coloration of the anodic coatings. However, they found out that they weren't durable. They would eventually fade out and get lost. And so, and when that was done, especially with aluminum colors. So aluminum colors initially, now remember, we're talking now at the end, we're talking, for the United States, we're talking about the Depression, all right? The stock market had collapsed in '29, there was a depression going on and so on, and aluminum colors gets this process, and they start utilizing the anodizing process. And initially, they're very successful with it. And the reason they are is because they're called aluminum colors. And what they did from the outset is that they took various aluminum products and they would anodize them, and then they would dye them. And I could get into a whole history of dyes, but the bottom line is that the initial dyes that they used were textile dyes. The aluminum dyes that we know of today were not developed yet. So he was using textile dyes. But the bottom line is that Helmer Bankston, okay, who was the owner, operator, and inventor, developed 8 patents associated with anodizing, and then later on we'll talk about some other patents that he did. But the bottom line is that he was successful for a while, and then eventually times got tough for him apparently. So now we have Alcoa stepping up, who has been successful with their aluminum. So Alcoa steps up and they buy his process, and they end up buying the rights for the anodizing process. And apparently they buy him as well, because there are a couple of patents in the list of patents in the back of my paper that refer to things that he did while he was with Alcoa. The patents were issued in his name, but assigned to Alcoa. So he was still working for them at the time they took that over. Now the interesting thing is, here again, the United States and Europe, all right, working sort of with each other. Alcoa then takes, okay, now this is 1928 till probably about the middle of the 30s. So about some 8 years later, what Alcoa does is they get a person from England who comes over and says, and he represents a consortium, and he wants the rights to get the rights, a licensing agreement basically, to utilize anodizing in England. But he does it only in his name, and he leaves the consortium holding an empty bag. But anyway, so Alcoa issues him the rights, or the license, excuse me, he takes it back and calls it Electrolytic and Alzac Limited. Now it's interesting to note, now we're about 1935, and it's interesting to note that today, in 2019, we still use the Electrolytic numbers and specifications for clear anodize and a matte finish, and we use the Alzac numbers, which is such as the R5 bath and so on, for bright depth finishes. So that process that Alcoa then licensed back both did matte finishes and bright depth finishes. So both of those, and we still are using those specification numbers even today in the literature. Meanwhile, Alcoa proceeded to license anodizing process. Then they went and took it to other European countries. They went to France, they went back to France, they went to Germany, and I think they went to they went to Norway, Sweden, and Denmark. And they went but there were 5 or 6 countries that they ended up then licensing the anodizing process into the European marketplace. And again, presumably with the Herald aluminum process, aluminum has been produced on a regular basis in Europe, so that when the anodizing processes came over there with the ability to do colors, they were ready for it, okay? And the products were available for them to start doing the anodizing. Now, let's go back to Reynolds. In the meantime, people were still smoking like crazy, so Reynolds Metals Company was growing through the Depression, okay? They continued to thrive during the Depression years, and eventually they developed the ability to print on aluminum foil and to laminate it with paper, and voila, they ended up producing covers for Eskimo pies and a huge variety of other things. Okay, so these things were all, but Reynolds Metals Company hasn't gotten into the anodizing business yet. Okay, they're still in the foil. They're caught up in the foil and the sheet and so on. But they're still an important player. Okay, now going back to Helmer Bankston, this is one of his patents, which I've used in talks before, because this is very interesting. This patent was issued in 1932, and all it is he got a patent for air agitation of his anodizing bath, okay? And we're all using air agitation today, but that's where the original patent came from, was back from aluminum colors in this Helmer Bankston, and he found that as he anodized, he had cooling going on, but he didn't have agitation of the bath itself, so it wasn't actually moving. And he found that the stagnant bath, the temperature would rise as the anodizing progressed, and the parts above would be warmer in the solution than the lower parts, and when he'd go into his dye tanks, those upper parts would absorb more dye than the lower parts, so he had a disparity in color through the load from bottom to top. And so he figured he needed to do something about it, so he came up with using compressed air to agitate that bath, and he eliminated that problem and corrected that issue. So if you ever dispute the value of air agitation, take it up with Helmer Bankston from 60-something, 70 or 80 years ago, right? 85 years ago. All right, World War II. World War II basically took charge of everything. All metals, okay? You know, all the metals were consumed in the war, essentially. You know, everything was focused on the steel and the tin and the aluminum and the copper. All of these metals were focused on what it took to build armaments, build materials, and so on to provide for the war effort, both in Japan and in Europe, in Germany. Well, actually in Europe, because it totally was over Europe. So basically, the general use of aluminum was diminished substantially. And construction applications and all this other places where aluminum was being used in the public interest basically ceased to exist or became very, very, very minimal. But all these reduction facilities were being built, and all these plants were being built that were able to produce products that would be towards the war effort. So at the end of the war, the government, the US government, had all these plants that were reduction facilities that they didn't need anymore. Okay, when they were done, they didn't need all these plants. So as a result of that, Alcoa said, well, we've already got all the plants we want. So Reynolds stepped up, and they bought several of those plants, of which one of them I eventually came to work at, which was in Troutdale, Oregon. And that was one of the reduction facilities that they had purchased, that they had acquired. Also, at this time then, Kaiser Aluminum and Chemicals Company came up and they said, hey, let's get into the aluminum business for whatever reason that they decided that. So in 1945, they stepped up and they bought some of those plants as well and became vested in the aluminum industry also. So now we have the Alcan of Canada, or Aluminum Company of Canada. We now have Alcoa, Reynolds, and aluminum vesting in aluminum seriously and significantly. So in post-World War II, the developments eventually with these companies, they said, hey, we've got a lot of metal. Now what are we going to do with it? We need to promote it somehow. Well, Reynolds found a wonderful way to do it. What they did is they created the aluminum foil, household foil market. They said, let's just sell the aluminum foil to all the housewives in the country. And you can go back and find videos of their ads of the ladies working, just like they did with microwaves when microwaves were first introduced, working with aluminum foil and doing all this cooking and everything and wrapping stuff up in aluminum foil and so on. And they successfully promoted Reynolds aluminum foil. And so they grew on that basis and became very successful. Alcoa continued to start pushing finishes, okay? And eventually Reynolds got drawn into it, Kaiser got drawn into it, and Aluminum Company of Canada. So they said, okay, let's find a way to promote aluminum. And they said, let's do it through finishes. and construction applications. So we're going to start, in this way, advances in extrusion technologies. We're now at a point where you could extrude aluminum in a variety of ways, huge variety. And they had the power to extrude the aluminum as opposed to tin and lead, which were softer. They now have the power to extrude aluminum. So they began doing this and promoting the finishes. And of course, the first finish they promoted was anodized finishes, or clear anodized finishes. And this was the common one during the 50s. This was the common one. And what I learned later is that there were attempts to utilize a method of coloring anodic coatings during this period of the 50s. Like I said, the original color applications that were defined in the first anodizing patent were not successful because they didn't produce stable colors. So they tried other things, and I'll get to that in a minute here in our talk. But the bottom line is that they came up with methods by which they could color the aluminum as well as market the clear anodizing. But the clear anodizing was the basic product. Okay, and out of that came an amazing design which Mr. Zahner was talking about. He was talking about the importance of alloying and how there's always a range and you have to match and all this kind of stuff and so on. But out of this clear anodized technology came an amazing product, and it's called the Air Force Academy. I'm sorry, I don't know what's wrong with me. Mainly because I was there in 1968 and saw it as a non-aluminum person, just a regular tourist, okay? So I looked at it when I was a regular tourist, and then I was invited back in 2017 after the conference in Colorado to come take a look at it as a non-tourist, but now as an aluminum expert. So I've had 55 years of experience with the chapel. So I guess that gets to me. I apologize for my sentimentality here. Anyway, it was built in 1959 and completed in 1962. It does exemplify what he was talking about. They were not real careful about the matching of what they called the planks, which are these parts that are run up and down here. And when I was there, you could see that there was quite a variation in those planks in brightness to matteness, and they just intermixed them at random. But the bottom line is, if you just go there and look at it, it's an amazing building, facility, and it's just gorgeous. And I encourage anybody to go there if they can. But when I went there and looked at it in detail, they asked me to look at detail. The amazing part, 55 years later, there was no external corrosion visible on the anodizing surfaces. You could see weathering that was on the actual surface itself that was superficial, but there was no actual corrosion to that. There's a slight patina that's developed over the years with that. And as a matter of fact, Zahner has been contacted about replacing that with 1 million pounds of aluminum. Okay, that building was constructed with 1 million pounds of aluminum. And they're going to replace that for mechanical reasons. The interior of it leaks like a sieve, unfortunately, when it rains. But during that time, it's on the eastern foothills of the Colorado Rockies, and I lived in Denver for 4 years, and I know what comes over the mountains. And it's just unbelievable. But that chapel has survived, and it's just a gorgeous example of anodizing that is done right and done well, and how it holds up. Okay. So the enhancement of finishes came back to dyes. Remember, aluminum color, okay, was using dyes for the finishes that they were doing in Indianapolis, okay, in Indiana, in the northern tier of states. And so dyes have been used successfully in Europe. And for those, you've got European members here, so people from Europe listening to what I'm saying, so don't hold my feet to the fire too much on this. But the bottom line is that in Europe, they use dyes for architectural exterior applications. Is that correct? You do, okay. Well, then we come to Richard Mahn's 37th parallel theory. All right, if you look at where Europe is located, how Europe is located, it's above this 37th parallel. If you follow the 37th parallel to the United States, you'll find that it crosses just at the base of New York, okay, and the upper Midwest, and goes across on the northern third of the United States and, of course, Canada. And we also saw an example of a building that was built in Minneapolis that was finished with red dye, okay, and is doing well because it's in this northern tier of sunlight-reduced environment. But what's happened in the United States is 60% of our U.S. is in areas where the sunlight is more intense, and then if you continue going to Mexico and Central and South America and so on, it gets worse, okay, for dyes. So the dyes don't hold up. So in the U.S., dyes have not been utilized for exterior applications. We have a huge market for all kinds of dye applications in the non-architectural marketplace. But for the architectural marketplace, they're not stable, they will fade, and if you're even if you're a northern supplier and you can't guarantee that your product isn't going to go south, you better not dye it. Okay, because if it goes to Florida, I guarantee you within 3 months, the red is not going to be red anymore. So we don't do that. So we can't use dyes in the U.S. because of that. Some of the dyes that we talk about that are utilized for various applications. This is an example of some of the things. And I remember, who was it? Not Zahner, Ziegler, that talked about grandma had the, where's the pointer on this? All right.
Should be able to hold down the middle set.
What happened to my pointer? There, no. Oh, dummy. Don't get old, okay? Please, don't get old. It's not fun. All right. He was talking about, grandma had these. Well, my grandma didn't have these, my mom had them, okay? And we drank out of those for years. But we had a set of those in the picnic basket, and I still have that set. Again, I'll probably start crying, but the point of it is that I have that set, and it's held up all these years, anodized and colored and kept out of the sunlight. But there's a lot of products that are done that are dyed and are very successfully dyed. So another innovation that was introduced at this time was the aluminum companies, again, promoting aluminum, pushing for aluminum, decided that they were going to push for aluminum cathodes in place, because all the tanks up to this time were lead-lined anodized tanks with lead coils for cooling, and so on. So they were going to push for the aluminum in place of lead-lined tanks and lead coils, and then external cooling to get the solution out of the bath and return it and cool it externally through heat exchangers. And so this accomplished three things for the aluminum companies. One, they sold more aluminum, okay, because they were out there replacing all these tanks with aluminum. And cathodes do dissolve gradually, so they have to replace more frequently. The lead would last indefinitely. It got rid of a potential health and environmental hazard, because once people started checking for lead in effluents, they found out that the lead was leaking off of the lead linings and everything else and getting into the waste effluent. So that became a negative. And then they found that it did actually improve overall the energy usage, conversion, and electrical efficiency of the process. And so it brought down cooling costs for refrigeration and so on, because the lead would actually be heating up during its process of anodizing. And the aluminum is 5 times more conductive. Plus it's lighter in weight overall. And you had to use much less of it, so you're putting much less metal in your tank. 60s was an amazing decade because so much happened in that period, in that time period. And one of the things that I was talking about earlier was in the 50s is these methods were tried, this double dipping where you dipped it into a metal salt bath, and cobalt was the one that I knew about. And then you would go to a potassium permanganate bath, and the potassium permanganate would reduce the cobalt metal, and you would get a light bronze. And then you'd rinse that and go back to the cobalt bath, and then you'd hold it in there for a while, you go back to the permanganate bath, and you go back and forth about 6 or 8 times, and you might end up getting to a medium bronze, which was a nuisance practice, obviously. Took a lot of effort. But this was a process that was commonly used in South America, Central America, and Mexico. Then I found out that the major companies are looking for something that they could color the anodizing coatings with, went to what was called metal sulfide precipitation. As we know, a lot of metals, when they come in contact with sulfides, become insoluble, colored materials. And they found that if they would do the same thing, do the double dip, they would soak it in the metal salt bath, and then they would go and dip it into a sulfide bath, sulfide-rich bath, and they would get a metal sulfide precipitate, and this would leave a coloration to the anodic coating. And so all of the companies, Alcoa, Reynolds, Kaiser, all did this. And somewhere after about 5 to 10 years, the color started deteriorating seriously. And as I understand it, you know, from the hearsay that I got, is they all ended up having to paint. They were sued and successfully, and they ended up having to paint the exteriors of some major buildings for several years until those buildings were torn down. So this turned out to be a massive negative for the major aluminum suppliers. And that left a bad taste in their mouth. However, not willing to give up, they ended up coming up with a new process. And this was a revolutionary process called integral color anodizing. And I was in a class not too long ago, and a bunch of young people, and I said, okay, who knows about integral color anodizing? Well, guess what? I was the only one who raised their hands, okay? Does anybody in here know what I'm talking about? There should be several people in here. But anyway, so the new revolution was integral color anodizing. Now, Alcan developed their process, but I didn't hear of any, I never ran into any of the process in the United States. It may have received some acceptability in Europe. That's a possibility, I don't know about that. But I do know that in the United States, Alcoa developed what's called the Duranodic or D300 process, and they came out with a series of 300 numbers that were bronze numbers, 310, 311, 12, up to 315 for the different bronzes from champagne to black. CalColor came up with, or Kaiser Aluminum came up with the CalColor process. That was marginally successful, not as many facilities as the Duranodic. And then Reynolds failed. Reynolds Color was not successful, so that was strike 2 for Reynolds. And this becomes important later. But that was strike 2 for Reynolds because they tried again getting into the marketplace with some kind of coloration process, and it didn't work. But in the meantime, Duranodic took over many and many plants in the United States. Also during this time, I don't know how to begin this one. I guess starting in the late 50s, well, yeah, the Apollo, or the Gemini project. Okay, first of all, Yuri Gagarin flew in space before we did. So no holds barred going forward. We're going to do research and we're going to get into space. So we have the Gemini project. Later on, we have the Apollo project and so on. But during that time, at the same time, in the late 50s, they actually had people that were sitting down and saying, we want to create a vehicle that we can send into space, circle the Earth, or do whatever we want with it, and then bring it back, have it actually fly back. And this was called the Space Shuttle Program by NASA. And this idea started in the late 50s. So in the early 60s, there became a competition of how are we going to coat the exterior part of the space shuttle with heat preventive materials so that when the space shuttle returns, it will burn up. So there was a competition between ceramic tiles and aluminum tiles. And Reynolds stepped up and started doing work on the aluminum tiles and coming up with a method by which they could anodize aluminum tiles, put a very hard, durable, abrasion-resistant coating on it, and also to whiten it and make it look white so that the emissivity and absorptivity properties of the tile would be competitive with ceramic. The unfortunate part, again, was that the white that was generated was not white. Okay, it was a translucent white. The white that you saw displayed today in the talk this morning is a beautiful white that's been put together, but even if you get up close to it, from what we saw, it looked white. But according to the person who does the work, it's a little bit frosty and it's not what you call the painted opaque white that we are used to. And that's the one that people have been demanding for years, ever since the word got out that you could do white anodizing. But anyway, the bottom line was, so that Reynolds came up with the use of organic additives in an anodizing bath, sulfuric acid anodizing bath, and if you used them in strong enough concentrations, you could actually anodize in batch up to 300 amps per square foot, which they did, and without burning the parts. Although most of the work was done around probably 30 or 24 to 60 amps a square foot. But anyway, the bottom line is that they came up with this work and they proved it out that it was successful anodizing, but unfortunately it lost out to the competition at the time. But out of that, they came up with what was called the MAE process. That's multi-purpose anodizing electrolyte. And what they then did, they got a patent on it and they marketed it license-free, no cost, but they would market it to people who used their metal, again, it was a marketing tool, and they would then allow people to use this process to create hard coats on parts without having to do it at 32 degrees. You could actually generate a hard coat that was equivalent to what was done at 32 degrees. You could do it at 60, 50, 60, maybe 70 degrees if you put enough of the additive in there. And this was known long ago with oxalic acid, that oxalic acid would create a hard coat finish, but it would discolor the coating. It would yellow it. So oxalic acid was basically one that was developed in China, or excuse me, in Japan, and they used it as a basis, and there's a patent, a Japanese patent, that identifies oxalic acid as one of the basic ingredients that they used in Japan for their anodizing processes when they started getting into the business after the war. So this MAE research and this additive and everything, this technology, then came out and they started promoting this additive for anodizing purposes to help promote their product. So they got back into the finishing. They were trying again to stay in the finishing business. Okay, electrolytic coloring. The proliferation of electrolytic coloring also, how do I say this, occurred in Europe, okay? Not the United States. It was occurring in Europe. And because integral color had taken over the marketplace. However, in Europe, you had Alcan now with offices in Banbury, England, who developed the analog system, which was, at first was nickel-based, and then eventually they switched to cobalt. You had Dr. Toshihiko Sato of Nippon Light Metals in Japan, who had developed an electrolytic process. You have Pechney in France. They used tin metal salts and stainless steel electrodes. And they did acquire a plant in the United States. Analog acquired 2 plants in the United States during this integral color time. Alu Swiss had a process. Henkel. So each of the individual European countries had their own electrolytic chemical or electrolytic coloring processes. And Ital Techno, represented here, and they had their process. And then Endasa of Spain, and they ended up coming into the United States, and they also had an anodizing company that utilized their process. So all these electrolytic coloring processes were available to the United States, but because of the success of integral color anodizing, they did not make huge inroads into the United States. They made marginal inroads into the United States. As far as I know, integral color never made any serious inroads into Europe. All right, now in the 70s, a significant thing was taking place, okay? All the kids that were born after the war were now in their 20s, and they were now consumers. And one of the main things that they consumed was electricity, because all of the companies were thinking about how they can sell to consumers. And so they were coming up with all kinds of electrical appliances, of which the worst, for our purposes, were air conditioners and electric heaters, which consumed a lot of electricity. And the net result was that the competition between the general population and industry got severe enough to the point that the electrical company says, hey, let's profit out of this. So what was used to be 2 cents a kilowatt hour became 12 cents a kilowatt hour. Okay, and they multiplied it dramatically. And also, if you were an industrial user of electricity and you used a lot of electricity during when the people wanted it, okay, you were penalized. And you would be penalized as much as $10,000 a month if you interrupted the electricity that was going to the consumer. So the first thing this did is this became a killer of aluminum reduction. In the 70s, the United States produced 80% of the aluminum consumed in the United States and overseas, wherever they sent it over, sold it overseas. By the 80s, the United States was producing barely 20% of the amount of aluminum that was being consumed in the United States. All of that aluminum was being imported from outside the United States from sources that had cheaper electricity to generate reduced aluminum.
You're working on the 2 o'clock.
We're getting close, right? I know, I understand. This is tough. All right, anyway, the serious deterrent became to architectural finishes because integral color anodizing required high voltages, high current densities, and was very expensive and took a long time to run those processes. So what happened was that Reynolds, one more time, got into the business, and they came up with a combination of the MAE process, German Keller electrolytic color chemistries, Getty German patent power supply, tin metal salts, and tin metal counter electrodes. And we went around and we literally, this is an example that's available to you from the AAC, one of their bulletins. But we literally revolutionized the integral color market and replaced it. So it essentially, through our efforts of the true color efforts and so on, we ended up replacing the integral color marketplace with electrolytic coloring. So now all anodizers, there may be a couple places left to do some integral color special anodizing, but all anodizers now use the tin process and electrolytic coloring process. This is an example of a bright dip, a buff bright dip part where the coating is very uniform and perpendicular, and then that's a black tin, or the tin that's in there to create a black electrolytic color. This is an electrolytic color bronze from the True Color finish process. Gold or light bronze and medium bronze. You can see the staggered colors on that one that was done deliberately to help balance off the fact that they couldn't get the color match exactly perfect, especially if you look across the top where they tried to do it with the colors and they had a little bit of variation. The next revolution that came, I'll have to make this short, so the next revolution that came, again, came from Europe. Okay, a lot of Europe comes to the United States, and some of the United States goes back to Europe. But in this case, The cold seal was developed in Europe, but it could not be used in Europe. At least that was my understanding at the time that it was brought to the United States in the early 90s. I was just leaving Reynolds in 1985 when one of my friends brought in a sample. He said, I just came back from Europe with this bottle of solution. They say it's a cold seal. And I didn't have time to do anything with it, but that was in 85. But in the 90s, this concept of the cold seal was introduced to replace the hot seal. The history is the hot seal was the hot water seal, later became a nickel seal, became a nickel mid-temperature seal, and now we have a nickel cold seal, which is done at about 90 degrees, not quite room temperature. But all of this reduced energy and time in the requirements of getting the sealing process done for the anodizer. The problem was, the negative part was that it required a curing time because it was cementitious material that required time to cure it out, and then it would create a brittle, non-resilient anodic coating. So this ended up being combined with a post-hot water seal. So you go back into a hot water seal, and the result was then you end up with a more resilient anodic coating. And now they're coming, and then also there was, because of the pressure against nickel, there were some seals that were developed that were mid-temperature or non-nickel, and I believe you're going to be talking about non-nickel cold sealing. Okay, so that's an innovation that's what we call a future innovations. Okay. Interference coloring, we got into a discussion about that. The fellow this morning was talking about the nano stuff and so on, and he said he sprayed it with gold, and he said he was surprised because he got all those colors. Well, that's what we call interference coloring. Now, let me get this clear. All coloring of anodic coatings is a form of interference coloring, okay? Because there's no color to the anodic coating, so by definition, if we color it, we're interfering with what is normally just totally reflected light. Okay, so it's all interference coloring. However, in this particular application, we're talking about special applications whereby you modify the pore base, and the phosphoric acid, as you anodize, you modify the pore base, and then you go into an electrolytic system, and then you put in a small amount of metal, and then that creates a green or a blue or a red or purple or burgundy or whatever, okay? The phosphoric acid step was created by Peter Sheesby of Alchem. The sulfuric acid step, using the modification step, was defined by Dr. Sato and Dr. Tajima of Japan. And then the using electrolytic coloring bath was by Dionisio Rodriguez of Spain. And the attempt to introduce integral or interference coloring in the United States was through the Spanish model, and a special power supply was created whereby it was connected to the electrolytic coloring bath. You did your normal anodizing, you put it in the color bath, you treated it with a special voltage to get the modification you wanted, and then you turned around and then you added the tin metal or whatever the metal was you wanted to create the color you were looking for. And this was attempted in the United States, and then one gentleman who's not in here, I don't think, asked the question about why it's not done in the United States. The bottom line is it was tried and it was not successful. It did not make it here. Now, again, I understand that in Europe there are some success with this, and 2 years ago I talked with a gentleman from Australia that says he does it very successfully. Aluminum Anodizers Council, oh, Jeff just came in, so you're ready for that part of it. Okay, so historically, since we're talking about history here, this is an important part because about the same time, the latter part of the 1980s, one of the things I wanted to stress is, remember I said Alcoa, Alcan, Kaiser, and Reynolds all were promoting finishes. After all of these experiences that the major aluminum companies had with finishes, they all stepped back. And my last job with Reynolds was when David Reynolds took the True Color process, which was extremely successful. Like I said, we successfully replaced all the integral color baths in the United States and several overseas. And he said, stop. because he'd gotten burned with anodizing in these previous applications. When he found out we were doing it, and he didn't know because we were Reynolds International promoting this, and he was Reynolds Domestic, and he said, stop, you're not gonna do it anymore. So what happened is, and this is important for you people in the anodizing business to understand, is that we, the suppliers, took on the responsibility of your care and feeding, okay? Because the major aluminum companies ceased to do that. You used to be able to go to the aluminum companies and say, we need help with this, or we need help with that, and so on. They aren't interested anymore, okay? So that's why we, the suppliers, typically are the ones who look after you and take care of you and want to help you. And in the meantime, then that meant that they weren't there promoting it, so a group of anodizers got together realizing they had to take on this responsibility themselves. So they got together and they formed the AAC, and in 1987, and then the first International Expo was held in 1991, and of course this is the 28th such expo.
We're gonna give everybody a break here pretty soon.
Yeah, okay. We can talk about the acid etch. I'm not going to go into detail on that because the technicalities of that have been presented by Linda Newman at various talks at other times. So that's another revolution that has, probably the latest revolution that has taken place in the anodizing or finishing industry over the years to present or create a uniform appearing finish to the benefit of all finishers. And then, of course, bright dip finishers, like I said, they have a history going back to the Alzac process in the 20s and 30s. There's some aluminum bumpers. We were talking about aluminum for automotive use. For about 20 years, probably 100 million bumpers were produced in the United States, okay? And then the automotive market said, we don't want them anymore. And so about 10 plants that were producing aluminum bumpers just completely shut down and went out of business. Conclusion. So the interesting part is that of the 4 major companies now, there are only one left, Alcoa, that identifies himself separately. Alcoa absorbed Reynolds, Rio Tinto absorbed Alcan, Pechney, and Audi-Swiss. Okay, but the basic anodizing process as we see it today has a lot of sophistications. We're doing a lot of things with it and a lot of modifications, but the bottom line is that first anodizing patent still drives everything that we do. It's still the basis of what we do. And the marketing factors for finishing are its durability and its appearance, and is considered to be more market value to the product. Anyway, that's the history of anodizing by Richard Mahn, a history of anodizing by Richard Mahn. And I want to appreciate your attention and happy anodizing.
Thank you.